Hey YouTube, thanks for visiting. So this is the last session of numerical analysis lecture series. Okay, I think this is the 10th lecture for the numerical analysis of GATE exam. Okay, so I am very sorry that I am not taking any class before the GATE exam. Okay, so this is the last session of or last lecture of the numerical analysis for the GATE exam. So I request all of you that please check the playlist. Okay, please check the playlist because I take some classes on live session and I take some classes on recorded session. Okay, so that's why you cannot find the playlist or the all videos of numerical analysis. So that's why I suggest that please go to the playlist section of my channel. Okay, and you get the numerical analysis playlist and you get the all the lectures one by one to 10th lecture. I think I already take 9 lecture and this is the 10th lecture of numerical analysis and this is the last session of numerical analysis. Okay, and in this session we are going to discuss the numerical linear algebra, that is the system of linear equations, the system of linear and algebraic equations. And in this chapter we have only 4 methods. Okay, one is the solution of system of linear equations, direct methods, and the direct methods are mentioned in the GATE syllabus, which are Gauss elimination and LU decomposition, and 2 iterative methods which are Jacobi and Gauss-Seidel methods. Okay, so we discuss these 4 methods one by one by taking the examples and some theorems regarding these methods. Okay, so let's start, and before starting I am requesting you to all that, so please those who are new in my channel, please like the session, comment if you have any doubt in the comment section below, and don't forget to subscribe the channel. Okay, so let's start. So first we discuss what is the system of system of equations. Okay, system of algebraic equations. A system of equations in n unknowns, that is the variables in is written as a11 x1 a12 x2. You all know that this is a system of linear equations, and these are here this is an n by n system of a matrix, you can say. In the matrix form we can write the system x as ax equal to b. Okay, so see, so the quantities x1 x2 xn are unknown, that is the variables of the system, and a11 a12 and amn are the coefficients of the unknown. So here mn, the order of the matrix is a m by n. Okay, a m by n. So the numbers b1 b2 and bm are constant or free terms of the system. Okay, so the above system 1 can be written as summation j equal to 1 to n a I j x j, this is equal to bi. So this is the summation form, and where I equal to 1 to up to m. Okay, so in matrix form it can be written as ax equal to b, where a is the m by n order matrix, coefficient matrix, b is the column vector, you can say, of m quantities, and x is the unknown variable terms or unknown variables. Okay, which are I think there will be x term, n terms here. Here it should be n. Okay, x1 x2 up to xn. Okay, now methods to solve the system. What is the methods to solve the systems? So there are basically 2 methods. One is direct method and another one is iteration method. And in the direct method, the methods are Cramer's rule, matrix inversion method, Gauss elimination, decomposition methods. This type of methods are comes in direct method. And in case of iteration method, basically the Jacobi iteration method and Gauss-Seidel method are 2 main iteration method or iterative method. Okay, so in the GATE syllabus, the mentioned syllabus is this one, Gauss elimination and decomposition, that is LU decomposition. And here one decomposition, I think 1 or 2 types of decomposition there are. Suppose Kraut's decomposition, Kraut's LU decomposition, and one types of decomposition, I forget the name just. And in the iteration method there are Jacobi iteration method and Gauss-Seidel methods in our GATE syllabus. These 4 methods are mentioned. Okay, so now we discuss these 4 methods one by one by taking the examples also. Okay, so let's start. Gauss elimination method. The first method is, this is the direct method. Okay, so this is the direct method, which is Gauss elimination method. So it says that in this method the unknowns are eliminated by combining the equation such that n quantities in equations in m equations, I think, sorry, m equations in n unknowns are reduced an equivalent upper triangular system which is then solved by the back substitution method. Okay, so first if we consider the 3 by 3 system, and then if we generalize the system, that is this will be very helpful to understand if we consider the 3 by 3 system. That's why I take here the 3 by 3 system first, and then we generalize the case. Okay, and this method is also mentioned in the book Jain Iyengar Jain. You can also follow the book of Jain Iyengar Jain, numerical methods. This is a very good book, and I say again that this content is made by using, I am using here the two books. One is numerical methods by Jain Iyengar Jain, and another one is numerical analysis by M. Pal or Madhumangal Pal. So the system, first we write a11 x1 plus a12 x2 plus a13 x3, this is equal to b1, and this is the 3 by 3 system, b1 b2 b3. There are 9 constant or 9 coefficient of the x1 x2 x3 term. Okay, so in the first stage of elimination, multiply the first row of 5, so this is the suppose system 5, by a21 by a11 and a31 by a11 respectively, and subtract from the second and third row respectively. We get what we will get? We get a1 to 2. This is the iteration. This is denotes the iteration. That is, sorry, this denotes the yes, iteration you can say, or this is 2, I think, second time. Just a minute. You can see this a12 is a what you can say, this is a notation you can say first. Okay, so this is equal to a12 minus a21 by a1 into a12. So this is first, if we read this line very carefully, multiply the first row of 5, that is this row, by a21 by a11, then you can easily see that this term goes to what? If we multiply this one, then this comes a11 into a21 by a11. Okay, so this a11, this a11 goes to cancel, so a21 into x1, and then if we subtract from the second row, then this x1 term vanishes. So this is our what we can say motto. Okay, to vanish the x1 term, to convert the system to a upper triangular matrix. Okay, so this is the case. Yeah, upper triangular matrix. So that's why we vanish these coefficients. Okay, so then a23 2, this is equal to a23 minus a21 by a11. So we, our motto is what? Our motto is to vanish these 3 terms, to convert the system in an upper triangular system. Okay, so that's why we multiply these 2 quantities and from then subtract from the second and third row respectively to get the upper triangular system, and these are the coefficients. A32 equal to a32 power a32 2, this is equal to a32 minus a31 by a11 into a12. Okay, and b1 b2 equal to b2 minus a21 by a11 into b1, and b3 equal to b3 minus a31 by a11 into b1. So these 2 quantities we can multiply with the coefficient and subtract from the second and third row respectively. Okay, in the second stage of elimination, multiply the first row in so I think this will in 6. Okay, in 6. So this is the system 6. So this is first step, we reduce the system. Then the second step is we multiply a322 by a22 and then subtract from the second row to get in 6. So in this case, from this we discard this coefficient or this term vanish, we vanishes this x2 term to get an upper triangular system, and then we apply back substitution method. Okay, so we get a33 x3 equal to b3. Now where a333 equal to a332 minus a322 by A22 into A232. Okay, and B3 equal to this one, B3 minus B32 minus B32 minus A32 to A222 into B22. Okay, so collecting the first equation. So if you forget this coefficient, you just remember that we have to convert the matrix in an upper triangular matrix. Okay, then you should definitely follow this rule. Okay, so this is our motto, to convert the coefficient matrix in an upper triangular matrix. That's why these are the operations. Okay, so collecting the first equation from the each stage from 5, 6 and 7. So this is the system 5. Okay, so this equation, taking this equation, taking this one and taking this one from 5, 6 and 7. Okay, we get these three equations, this one and this one. Now we first find, now the system 8 is an upper triangular system and can be solved by using the back substitution method. Back substitution method means first we find the value of x3, that is from here we can write x3 equal to b33 by a333. Okay, then put the values of x3 here to get the value of x2, and putting the value of x2 and x3 in the first equation we get the value of x1. Okay, so this is the back substitution method. So A given B by Gauss elimination method is converted to a matrix which is U given C, or U is an upper triangular matrix. The elements A11, A122 and A33 which have assumed to be non-zero are called pivot elements. Okay, so A2111, A222 and A333. Hence this is the stage of operation. This is first stage of operation, this is the second stage of operation, and this term is the third stage of operation. Okay, so in general denote BIK, this is equal, so this is the case for 3 by 3 system. Now if we generalize the system, then we get BIK, that is kth operation, this is equal to AIK, AI n plus 1, AI n plus 1 k, or IK equal to 1 to n. Okay, and AIJ k plus 1, this is equal to Aij k minus Aik k by Akk k into Akj k. So this is the generalized. So you can't remind this thing, or you can't remember. If you remember, then this is very good, or if you forget these elements, then no matter, you just do, or you just convert the coefficient matrix to an upper triangular matrix. Okay, this is your motto, or our motto. Okay, so the elimination is performed in n minus 1 steps, k equal to 1 to n minus 1. In the elimination process, if any one of the pivot element or pivot element, this vanishes or becomes very small as compared to their elements in that column, then we attempt to rearrange the remaining rows so as to obtain a non-vanishing pivot, or to avoid the multiplication by a large number. This strategy is called pivoting or pivoting. Okay, and there are two types of pivoting we mainly apply here. One is partial pivoting and second one is complete pivoting. So what is partial pivoting? Here it says that in the first stage of elimination, the first column is searched for the largest element in magnitude, okay, and brought as the first pivot by interchanging the first equation with the equation having the largest element in magnitude. Okay, in the second elimination stage, the second column is searched for the largest element in magnitude among the n minus 1 elements, leaving the first element. Okay, so and the element is brought in the second pivot by interchange the second equation with the equation having the largest element in magnitude. Okay, this procedure continued until arrive the equation, simple ninth equation. This is the book equation, so equation number 9 here. Okay, which is this one. Okay, we are thus led the following algorithm to find the pivot a j k k. This is equal to max of a I k k. Okay, so that means what? That means the smallest integer for which, that means suppose this is the matrix. Okay, suppose this is the matrix. First we see the which one of the first element is having greatest magnitude. We convert this row to the first one, then we find the second this column, we see the second column and find the largest coefficient in magnitude and put it in the second as a second row. Okay, and continue this process. So this is the pivoting. What is complete pivoting? We search a matrix A for the largest element in magnitude R being as the first pivot. Okay, this requires not only as interchange the equations but also interchange the position of the variables. Okay, this leads to the following algorithm. The algorithm is choose L and M as the smallest integer for which a lm k this is equal to make maximum of mod of, that is the magnitude of a ij k, where k less equal to ij less equal to n. Okay, and interchange rows k and l and columns k and m. So that means in this case we need to change as well rows as well as the columns. Okay, now taking an example, and this is the book of Jain. Okay, so solve the equations. This one 10 x1 minus x2 plus 2x3 is equal to 4, and this one and this one. Okay, by Gauss elimination method. The system is diagonally dominant. Okay, what do we mean by diagonally dominant? So this is a very important word, and no pivoting is necessary. Diagonally dominant means what? The value of the diagonal element, that is a11, is greater than sum of the other two elements in magnitude. That is, this coefficient is -1, that is we sum -1 plus this is simple 2. Okay, so here this means 10 is greater than 1 plus 2 is equal to 3. That is, this is true. So that means this is diagonally dominant. Okay, the diagonals element are much greater than the sum of our other two elements in each row in magnitude. Okay, so that means if you see this system, then this system is a diagonally dominant, or this coefficient matrix is a diagonally dominant matrix. That means we don't need to pivot, or we don't need to pivoting. Okay, so we have, after the first elimination stage, we get a 10 x1 minus x2 plus 2x3 is equal to 4. Then this is okay, 101 by 10 x2 minus 12 by 10 x3 is equal to 26 upon 10. That is, we need to convert this system in an upper triangular system. Okay, step by step. And then this one in the second stage, that is, we multiplied what? We multiplied by these terms. Okay, we multiplied this a11 by this term a22 minus, or a22 equal to a22 minus a21 by a11 into a12, and get this value. Okay, and get these values. And similarly, if we apply the second process or second stage of elimination, then we get this one. And now we back substitute the values x3 equal to x3 from this equation we get the values of x3, then we put the values of x3 to this equation to get the values of x2, and then we put the values of x2 and x3 in the first equation to get the values of x1, and the solution is this one. Okay, so this is the simple Gauss elimination method. You just remember one thing, that we need to convert the coefficient matrix in an upper triangular matrix, and then just solve the system by back substitution method. Okay, suppose if we see the system, suppose this is a 3 by 3 system, this is non-zero, this is non-zero, and this is non-zero, this is non-zero, this is non-zero, this is non-zero, and all other elements are 0. That is, this is an upper triangular system, and this is x1, x2, and x3. This is equal to, suppose, b1, b2, b3. You just remember this thing. So this into this is equal to b1, this into this is equal to b2, and this into this is equal to b3. So these two terms are 0. That means this into b3 x3 gives you b3. Okay, after elimination. Okay, so this is the case. Now we're going to the second method of direct method, which is LU decomposition. Okay, so in this method the coefficient matrix A of the system of equations Ax equal to B is decomposed or factorized into the product of lower triangular matrix L and an upper triangular matrix U. We write the matrix A as A equal to L into U, where L equal to, this is the lower triangular matrix, L11, L12, L22, L31, L32, L33, and this is the last row. And similarly U is equal to the upper triangular matrix U11, U12, and this one UNN. Okay, now using the matrix multiplication rule to multiply the matrices L and U and comparing the matrix elements of the resulting matrix with those of A, we obtain what? Li1 U1j plus Li2 U2j plus plus Lin Unj, this is equal to Aij. Okay, and j equal to I equal to 1 to n, this is number 1, where Lij is equal to 0, j greater than I, and Uij equal to 0 for I greater than j. That is, this is the definition of upper triangular matrix. Okay, now the system of equations involves n square plus n unknowns. Thus there are n parameters family of solutions. To produce a unique solution, it is convenient to choose either Uii equal to 1 or Lii equal to 1 for I equal to 1 to n. Now for Kraut's LU decomposition, which is in our syllabus, we choose Uii equal to 1. Okay, the solution of the system 1, this is equal to Lij equal to A1j minus summation k equal to 1 to j minus 1 L ik into ukj. Okay, and Uij equal to this one, and Uii is equal to 1. So we just read the theorems. If you say that this is the difficult, so this is something difficult because there are some big notations. Okay, so many notations you can say, but if we take the example, then this is easy for you. Okay, so that's why I first just once repeat the theory part, and then we taking the examples to understand the methods very easily. Okay, so note that the first columns of the matrix L is identical with the first column of the matrix A. Okay, that is Li1 equal to Ai1, I equal to 1 to n, and U1j is equal to A1j by L11. Okay, the first column of L and the first row of U have been determined. We can choose now proceed to determine the second column of L and second row of U. Okay, so this is the second row, Li2 equal to Ai2 minus Li1 U12, and L2j, this is equal to A2j minus L21 U1j by L22. Okay, we find the third column and of L by following the third row of U. So we find one row of L, that is the lower triangular matrix, and one row of the upper triangular matrix. These types of operations we using here to find the matrix L and U. Okay, so computed in order, Li1 U1j. So this is column of L and row of U, column of L and row of U, first column of L and first row of U, second column of L and second row of U, in this way. Okay, so having determined the matrices, so suppose if we write the matrix L and U, suppose this is L, this is U. So we first find this column and this row, then this column and this row, this way. Okay, this is the way to find L and U. The equations Ax equal to B becomes Lux is equal to B. We can write the above as Ux equal to Z and Lz equal to B. Okay, 2 and 3. The unknowns Z1, Z2 and Zn are determined by the following forward substitution, and the unknowns x1, x2, xn in 2 are obtained by back substitution. Alternatively, we find L inverse and U inverse to get Z equal to L inverse B and x equal to U inverse Z. Okay, and the inverse of A can also be determined from A inverse equal to U inverse L inverse. Since A equal to L into U, so we can find A inverse, this is equal to LU inverse, which is equal to U inverse and L inverse. Okay, this method fails if any of the diagonal elements Lii or Uii is 0. That means what? The LU decomposition is guaranteed the matrix when the matrix A is positive definite. However, it is only sufficient condition. So this is very important line. Okay, matrix is positive definite means what? All the eigenvalues lambda is are strictly greater than 0. Okay, so LU decomposition guaranteed. So if the positive definite, if the matrix is positive definite, then we definitely find the LU, L and U. That is that we definitely decompose the matrix A in L and U, that is one lower triangular matrix and one upper triangular matrix to solve the system. Okay, and remind that this is only a sufficient condition. Now let us take an example. X1 plus x2 plus x3 equal to 1, 4x1 plus 3x2 minus x3 is equal to 6, and 3x1 plus 5x2 plus x3 this is equal to 4. Now choose u11 equal to 1. We write here. Okay, so this is equal to the coefficient matrix, which is equal to, we write L into U. Okay, now L, this is L11 into 1, so L11, so L11 equal to 1. If we compare, then we get L11 equal to 1. Then what? L11 into U12, this is equal to, we get this 1. Okay, now if we comparing, then we get these values. L12 equal to what? L12 equal to 4, L21 equal to 4, and L31 equal to 3. So we first get the column, first column of L. Okay, L11, L21, L31, the first column of L. Then first row of U, then we get the first row of U. So L11 into U12 is equal to what? 1, and we put the values of L11 to get the values of U12. Then L11 U13, this is equal to 1, and if we put the values L11, then we get the value of U13. Okay, so this is first column of L, first row of U, then second column of L, then second row of U. We get all the values of U and L to get the matrix, a lower triangular matrix and one upper triangular matrix. Okay, now using forward substitution, we get Z equal to this one, 1 minus 2 and minus 1 by 2. This is a column vector, and the back substitution we get x1 x equal to 1 1 by 2 and minus 1 by 2. So this is the answer of the system Ax is equal to B. Okay, so this is the system. Okay, now going to the next method, which is iteration method. So Jacobi iteration, and here if we see the back forward substitution method by using these ones. Okay, what? These two, Z equal to L inverse B and X equal to U inverse Z. That is, we first find Z, and then by using Z we find X. Okay, so X equal to what? L inverse B. Okay, we can easily find the value, we can find easily the L inverse, because this is an lower triangular matrix. Okay, okay, now we're going to the iteration method, and first one is Jacobi iteration method. Okay, first one is Jacobi iteration method. Jacobi iteration method. So let Ax equal to B be a system. Assume what? The quantities Ai in equation 1 are pivot elements. Okay, so A11 x1, this is equal to this one, we can write, suppose if we write A11 Ax is equal to B, that means what? A11 x1 plus A12 x2 plus dot 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 plus A1n xn, this is equal to B. Therefore A11 x1 equal to this is the minus term, A11 x1, this is equal to minus of A12 x2 plus dot dot plus A1n xn plus B, this one. Okay, so we write this system is this in the form of this. Okay, now the Jacobi iteration method or Gauss-Jacobi method can be defined as x1 k plus 1th iteration, this is equal to minus 1 by a11 into this one first term. From this step, okay, just we put the values a11 in this side or right side, then we get the values of x1, then we get the values of x2 k plus 1th iteration and xn values k plus 1th iteration. Okay, so this is the iteration methods, which is the Gauss Jacobi method or simply Jacobi iteration method. Okay, in the matrix form we can write x k plus 1 equal to minus d inverse L plus u x k plus d inverse b, this is equal to h x k plus c. So this is the Jacobi iteration scheme, you can say, and this h is the Jacobi iteration matrix. Okay, h is equal to this one minus d inverse L plus u c equal to this one, and this h is known as Jacobi iteration matrix. Now how it comes? So if we write ax, this is equal to b, now we write a is equal to what? So a is equal to, if we write d plus L plus u, d is the diagonal matrix, L is upper lower triangular, u and u is upper triangular matrix. So if we put this a is equal to d plus L plus u, so we get d plus L plus u into x, this is equal to b. Okay, so this is dx, this is equal to minus of L plus u into x plus b. Okay, now we get x equal to d inverse minus of L plus u into x plus d inverse b. This is the Jacobi iteration scheme, how it comes. Okay, from the system ax equal to b. Okay, and L and u respectively are the lower and upper triangular matrices with the 0 diagonal entries, and these the diagonal matrix such that a is equal to a plus d, L plus d plus u. Okay, so this is the iteration scheme. We can write x k plus 1 is equal to xk minus I plus d inverse a plus u into xk plus d inverse b. Okay, so xk is equal to xk plus 1 equal to xk plus d inverse into b plus a x power k. Okay, this is the iteration scheme. Now if we take an example, solve the system, this one 4x1 plus x2 plus x3 equal to 2, x1 plus 5x2 plus 2x3 is equal to minus 6, and x1 plus 2x2 plus 3x3 is equal to minus of 4. So given the initial iteration which is equal to x0 equal to 0.5 minus 0.5 and minus 0.5, this is column vector. Okay, so L is equal to, we can write the lower triangular matrix, so 1 this term 1 1 and 2 and this 3. Okay, this is the lower triangular matrix, and diagonal matrix is simply 4 5 and 3. This is the diagonal matrix, and what the upper triangular matrix is 1 1 and 2. This is the upper triangular matrix, 0 1 and 2. This is the upper triangular matrix. Okay, no, I think this is 0, this is the lower triangular matrix. Okay, so h equal to d inverse L plus u. So d inverse means simply this is since diagonal matrix, so inverse is same. Inverse is simply 1 by 4, 1 by 5 and 1 by 3, and this is the L plus u terms. Okay, so this is d inverse and this is L plus u, and this gives 0 minus 1 by 4 minus 1 by 4 minus 1 by 5, 0 minus 2 by 5 and minus 1 by 3 minus 2 by 3 and 0. So this is the H matrix, which is the iteration matrix. Iteration matrix. So questions in the GATE exam comes from this iteration matrix. Okay, so this is very important. Okay, then C equal to D inverse B, we get simply the C equal to D inverse B, which is equal to 1 by 2 minus 6 by 5 minus 4 by 3. So Jacobi iterations methods becomes x k plus 1 equal to a x power k plus C, which is D inverse B. Okay, now starting with this x0, so we put the values x0 is initial position to here to get the first iteration. So we get, if we simply put this initial vector to this position, we get simply x1 equal to this, and then put the values of x1 to get the second iteration x2, this is which is this one, and the third iteration we put the values of x2, we get the this one. Okay, so simply we put the initial values and then the next values and then the next values of x to get the iterations one by one. Okay, so this is the scheme, and alternatively we can write directly xk plus 1 equal to 1 by 4 into 2 minus xk minus x 3 power k, and x 2 k plus 1, this is equal to, that is k plus 1th iteration, which is equal to 1 by 5 into this one, and x3 equal to this one. Okay, so if we see the matrix or coefficient matrix, so we simply write, so from here, okay, x1 equal to, we can write x1 equal to 1 by 4 into 2 minus x2 minus x3, and this is k plus 1 we write, and these two we write k and k. Okay, and from this one we get 1 by 5 into this one, we take x2 from the diagonal elements, we can say. Okay, okay, now if we put the values of x0 term, that is initial vector, then we get the first iteration, then we put the x1, then we get the second iteration. If we put the values of x2, then we to this system or to this scheme, then we get the third iteration, and similarly we can calculate the so on the next iterations also. Okay, now so this is the Gauss Jacobi method or Gauss Jacobi method. Now it comes to the second method, which is Gauss Seidel method, iteration method. So this is basically same as like Gauss Jacobi method, but there is some difference between Gauss Seidel method and Gauss Jacobi method, which is, देखो यहाँ पर क्या है, from the above we can write x1 k plus 1 equal to this one. Okay, so we use here the above iterations, the values of x1, x2 and x3, the values of other xi's, we put the above iterations values. Okay, but in the Jacobi or Gauss Seidel method, we use the, suppose we calculate x1 first from using the iteration, then we find the values of x2, and here in the terms of x2 the value of x1 is included, then we put here in the Gauss Jacobi method we use the above iterations xi's, but here we use the xi's in the iteration which is we just find. That means if we find x2 x1 k plus 1, okay, and in the terms of x2, suppose here one x1 is included in the iterations of x2, in the first iteration we use the values of xk plus 1 here, but in case of Gauss Jacobi method we use here the x1 power only k, that is the kth iteration method, that is the above iterations value, but in this Gauss Seidel method we use the same iterations values which are already defined, that is the above values of the variables. Okay, this is the difference between Gauss Seidel method and Gauss Jacobi method. Okay, so if we see the example, then we can easily understand this one. This is the questions from GATE. Okay, so by using the Gauss Seidel method, here the initial iteration is given. So first we write the iteration scheme. So x1 k plus 1 equal to 7 plus x2 by 1 by 2. This is the iteration scheme. Okay, now first approximation for k equal to 0, use the x1 0, x2 0 and x3 0 to here. So x1 1 equal to 1 by 2 into 7 plus x2. x2 means what? x2 means this one, x2 power 0 means 2.25. okay, this is equal to this one, and we use now the x1 power k plus 1. Here see, in case of Gauss Jacobi method, here we use xk, x1 power k, but that is the k iteration, that is the above iteration. But in case of Gauss Seidel method, we use the same iteration, so we use the values of same iteration, that is, this is suppose one iteration, we find or we use the values of xk plus 1th iteration value. So this is more improved method as compared to Gauss Jacobi method. Okay, and then we use x2 power k plus 1 also. We just find the k plus, this is the value we get from the same iteration. Okay, that is the k plus 1 iteration values. Okay, so this is the difference, and we put the values to get this x1 x2 x3, the same iteration, second approximation. Okay, so this is very easy, we just put the values. Okay, now convergence of iteration method. So this is a very important concept, which is convergence of these iteration methods. Okay, so suppose Ax equal to b, and we put the values of this and we get this one is the iteration scheme. Okay, where h is equal to, we already know that. Now first theorem says that the iteration method is of the form xk plus 1 equal to h xk plus c for the solution of Ax equal to b converges to the exact solution for any initial vector if norm of h is less than 1. Okay, here norm is included. So if you want about the different types of norm of numerical analysis, then one dedicated video is already made. I already made a dedicated video in norm. Okay, I give the link of the video in the description of this video or this lecture. Okay, you just click the link to watch the norm case. Okay, or numerical norm vector or different types of norm in numerical analysis. Okay. And the norm is also very important for numerical analysis. Okay, so you can definitely check once. So the next theorem says that a necessary and sufficient condition for the convergence of the iteration method of the form, this is the iteration method, is that lambda I h is less than h, that is all the eigenvalues of the iteration matrix h is less than 1 and which is in magnitude. Okay. Next theorem says that if h is strictly diagonally dominant, then the Jacob iteration scheme converges for any initial vector. Okay, so what is strictly diagonally dominant matrix? I already say what is diagonally dominant matrix. So I just write here, for any matrix A is said to be diagonally dominant if Ai modulus of Ai is greater or equal to the all other terms or all other elements in the row. Okay, holds. Okay, A is said to be strictly diagonally dominant if here only strictly greater than holds. Okay, so this is the definition of diagonally dominant matrix. The next theorem it says that if A is strictly diagonally dominant matrix, then the Gauss-Seidel iteration scheme converges for any initial starting vector. Okay, so these theorems are regarding the convergence of iterations method of, that is the Gauss-Seidel method and Gauss-Jacob method, or simply Jacob iteration method. Okay, so this ends today's class, and this is the last session for numerical analysis or the lecture series NA for the GATE exam. And so this is the theory lectures. I think there are 10 lectures, and this is I think 10th lecture. 10 lecture. Okay, total 10 lectures there are for numerical analysis of GATE exam, and this is also helpful for CSIR NET exam and SET exams also, because the GATE syllabus of numerical analysis is the very big syllabus as compared to CSIR NET syllabus or any other state level SET exam syllabus. Okay, so this lecture series is very helpful for GATE exam obviously, and also for the CSIR NET exam and the any state level SET examination. Okay, so I think this lecture series is helpful for you. So if this lecture series is helpful for you, then please give like and share with your friends to the lecture series. Okay, so thank you for watching, and I already take the classes on the previous years questions of GATE exam of numerical analysis, and you can comment me in the comment section below of this video that the next topic you can choose. Okay, to the for the GATE lecture series. I think or I just think once that the calculus part, if we take, what it will be, कैलकुलस फॉर गेट, ये कैसा क्या होगा, मतलब ये हेल्पफुल होगा कि नहीं, आप लोग एक बार कमेंट सेक्शन में ज़रूर बताइएगा. ठीक है, कैलकुलस को लेकर आई थिंक डिस्कस करेंगे. मतलब मैं सोच रहा था कि कैलकुलस को लेकर थोड़ा डिस्कशन करेंगे और लेक्चर सीरीज एक बनाएंगे फॉर गेट एग्जाम. ओके, बिकॉज कैलकुलस इज ऑल्सो वेरी इंपॉर्टेंट फॉर गेट एग्जाम. ऑल कैलकुलस. ओके, फर्स्ट वेक्टर कैलकुलस, देन differential calculus, and then integral calculus also. Okay, so this ends today's session. Thank you for watching. Thank you.